Hey everyone, this is Dr. Walker. This is video 47C on momentum. Let's start by defining this new quantity called momentum. It's defined as the product of an object's mass and its velocity. Momentum we use the letter P for momentum. It's defined as mass times velocity. If we look at this picture here, we see this big boulder going after this poor man. So the big boulder here is in motion, it has velocity, it also has a large mass, so it has a lot more momentum than the man that is running. We look back at momentum here, we see that its units are kilograms times meters per second, which comes from mass and velocity, and we note that momentum is a vector. The fact that momentum is a vector will allow us to solve problems that we haven't solved before, such as problems dealing with collisions and explosions. Let's go back to Newton's second law for a second. Remember Newton's second law, what it said? It said the sum of forces, right, the net force equals ma. Well, now let's rewrite it. Let's rewrite the acceleration as the derivative of the velocity with respect to time. And now, let's go ahead and bring the mass inside the derivative. So we have the derivative of mv with respect to t. That's the net force. So what we see here is that the time rate of change of the linear momentum of a particle is equal to the net force acting on the particle. Because look, the net force is equal to the derivative or the time rate of change of mv, which is the momentum that we just defined. That is momentum. So this is another way to write Newton's second law. Time rate of change of linear momentum of a particle is equal to the net force acting on a particle. Now, before we finish this video, let's also talk about what is an isolated system. When we were dealing with energy, an isolated system was one in which there was no transfer of energy into or out of the system. But now when we're dealing with momentum, an isolated system is defined as one in which there are no external forces on the system. So for instance, if you define your system as these two masses here, well, we know that they both have a gravitational force, right? They both attract each other. We have action and reaction forces. So those would be internal forces that are part of the system. If there's no external forces, nothing external pushing on any objects or anything like that, then it's an isolated system. I do want to mention that whether a system is isolated or not depends on how you define the system. For instance, take a ball. If your ball is your whole system, then that is not an isolated system because there's a gravitational force acting on it, right? So that would not be an isolated system if your system was just the ball. But if you have a ball and the earth, and you define the whole thing as your system instead of just a ball, well, now you can say, well, that gravitational force that they both exert on each other, that's an internal force, and now the whole system is indeed isolated. Let's take a look and see what happens when we do have an isolated system. If we go back to Newton's second law that we just wrote, the sum of the forces, the net force, was a time rate of change of the linear momentum, derivative of p with respect to t. Well, now we're saying there's no external forces on the system because we have an isolated system. Well, we cross out the forces here, set them equal to 0. What does this mean? This means if your derivative is 0, that means that you're taking the derivative of a constant. So that means that this momentum here, we can say the total momentum, is constant. And that is really, really, really important. It actually leads us to conservation of momentum, which we'll get to in video 49. But what we're saying, if the momentum is constant, there's no change in the momentum, then we can write it like this. The change in momentum is equal to 0. This is conservation of momentum. I wanted to introduce it now because I wanted to talk about an isolated system, because in the next video we will have non-isolated systems, so I didn't want that to come out of nowhere. But we will come back to this idea of conservation of momentum in video 49. But before we go to the next video, I have one more question for us. We are looking for the card's change in momentum. It's only moving in the x direction, so the momentum is only in the x direction. Can you pause the video and figure out what is the change in momentum of this card? All right, so remember, change is final minus initial. So we are looking for the final momentum minus the initial momentum. And we're just all in the x direction. Still write it as vectors. It's all in the x direction. So what are we going to put for the final momentum? Well, it's a mass times velocity. The mass is 10 grams. But we'll just call it m for now, right? M times Vf minus m times Vi. The reason I put this example here is because it is super important to remember that momentum is a vector, and whenever you're dealing with vectors, you have to pay attention to direction. Velocity has a direction, and so many people forget to pay attention to that. So that's why I have this example. So what you should write down here is that the final velocity is 1 meter per second, and then the mass is 10 here, 10 kilograms, but the initial velocity, don't put 2 here or you're going to get the wrong answer. Because it's going to the left, we have to say that the velocity is -2, right? The speed was 2, but the velocity was -2 meters per second. It has to have a direction opposite of our final velocity. So when you plug in 10 minus a -20, you end up with a positive 30 kilograms times meters per second. Another reason I wanted to do this example is because we're going to see change in momentum very, very often, starting in the next video.